chemistry important, right? Okay. All right.
From the novel, he's the cardiologist.
All right, you guys. So, this is carbon. H2O is water. Carbohydrate. I know that for some of you this is not new news, but that is the basic fundamental formula of carbohydrates. How will most of you recognize carbohydrates?
Rings.
Rings, are they always in a ring structure? No.
Not necessarily.
Carbon, hydrogen, oxygen, and the oxygens are usually, and hydrogens are a lot of alcohols on them, right?
Yeah.
Okay. Yeah, so good. There are some, they're produced by photosynthesis. By the way, when plants pull in CO2, this aha moment should be, your seniors, this should be easy for you. Plants pull in CO2, and do they turn that CO2 into oxygen, yay or nay? Tell your neighbor.
Yes. Photosynthesis.
No, they turn it into sugar.
Yeah.
If you answered yes, go back to biology, you are wrong.
Oh, wow. He let me go with it too.
It turns out that the CO2 is directly turned into sugars. Well, then where's the oxygen coming from?
Water.
Water. Oh, okay. So I eat carbohydrates, okay? I eat them. They're delicious, right? And then when I eat carbohydrates, I breathe out CO2. Great. That's fantastic. And, but I'm breathing in oxygen. Where's that oxygen going? Say it? Into water. The end of your electron transport chain has oxygen and it turns it into water. If you never heard that, time to grow up. We got to figure this out. Somebody back there in grade school ruined you for life.
Guess I shouldn't
And an
graduate
oversimplification problem. Okay. There are some carbohydrates that are huge, 2 million grams per mole. Wow. Okay. Some are really small. 90 grams per mole. Variety of functions, yes, energy storage, building cell walls with them, right? Exoskeletons of bugs, also lobster and crabs, right? Also signaling molecules, informational. This last one we'll talk about near the end. It is the complexity. If you really want to know a Nobel Prize worth getting, it would be to break what we will talk about as the sugar code, where you really can decipher it and use it. We have the tools to use it, because its complexity is something that currently we know it's there. We have the way to probe it a little bit, but not enough to do what's actually there. And it is holding us back. So we got to figure this out, okay? What does this functional group tell your neighbor?
Which one?
After you tell them that, name this functional group.
And it's what's an aldehyde.
Oh, I mean,
Is what they're looking for. And aldose is the sugar.
It is on the slide, right? Just in case you're wondering.
And they look at the ketones.
Duh.
Yeah.
Aldehyde, ketone. Okay, if you named it carbonyl, that's good, but it is a ketone in the way it's written. All right, so we have both forms of carbohydrates that we're interested in. When we learned about amino acids, what was the most common chiral component? What was the most common of amino acids? Did we go D or L?
Oh, it was,
Definitely L,
Yeah.
right? The way it rotated like. What if we talk about carbohydrates?
isn't it D?
D is the one that we like for carbohydrates. I have no idea why it got set up the way it did, but it'll be a great question to ask the maker, right? And he's like, why did you choose that? And he may say, oh, I rolled the dice. I don't know, maybe he's got it, maybe
He's like,
got it
"Ah, I
right.
got tired of that."
But he definitely stuck to largely one in both of those, we're dealing with, okay? So, ribose. You'll want to know ribose in linear and in cyclized form, okay? Deoxyribose and ribose. What is really the difference between those two? Tell somebody else that you're smart enough to know where deoxyribose and what it actually means is compared to ribose.
So the fourth carbon is missing in hydroxyl group and deoxyribose. I think it's the fourth. Oh, sorry, no, it's the second one.
Okay.
Actually. And
Well,
then
can't you write these?
You have
down?
it.
It means I have
counted the wrong
lost
way.
Yeah.
an oxygen.
Yeah.
It's like the chemistry speaks to me in language. Deoxy. It's always at the 2' position. That's the one we're interested in. Where do we see that? DNA, right?
And RNA.
And RNA's the other
Ribose.
form. Yeah. So we'll deal with that. Okay. Enantiomers that we're dealing with, we are interested in talking about sugars, D or L. We will be looking at the last chiral carbon on that, which is still in the chain, the one furthest from the carbonyl. Okay. Let's see. Where did we get this idea of rotating light? Well, it comes back to glyceraldehyde. They really didn't know when they were separating them out what was going on, but they did confirm that they guessed right, okay? So based on the location of the alpha carbon amine group, L is on the left and D is on the right going down, okay? L versus D. Yeah.
So to confirm that the way that they did it is they replaced the hydroxyl group with an amine, and then they used the charge to figure out which way it was facing.
That's really what we ended up doing with our amino acids, right?
Yeah.
Yeah, but when we were starting here, these chiral centers
Yeah.
actually do hold with the way the light's rotated.
Okay.
These don't always hold up,
Okay. Okay.
okay? But when we were drawing the amino acids, you knew if it was to the left, that was definitely my L, and to the right was my D. And so that means that when you're looking, is this a chiral carbon?
No.
Okay, this is not, but is this one?
Yes.
Yes, absolutely it is. So the last chiral carbon from the, going down the chain, that's the one we're interested in. Okay, so based on that, you should easily be able to define which one is D, which one is L. It also says on the name of it, right? Okay, please be able to do that on the upcoming exam. We'll practice that a little later today. This should be easy, okay? Left side, right side, okay? Diastereomers are not the mirror images that we're looking at, okay? Water solubilities can change when we're looking at these. There's ribose, again, you need to know that one. It will be one of 3 structures that I will have you learn. The other being glucose and fructose. And you'll need them in both their linear form as well as their cyclized form. It turns out that you'll be learning to cyclize, so you can just learn one and it will be okay, as long as you can go back and forth. So you don't need to learn 6 things, just 3 there. An epimer is when 2 sugars differ only by the configuration around 1 carbon. Given this, there's a question, a homework, a question that would be in the book. It says identify all the epimers of D-allose. Here is D-allose. Work with your team and identify all the epimers of D-allose. Again, what you're looking for is that the 2 sugars differ in the configuration around just 1 of the carbons. not multiple, just one.
So it's altrose,
Altrose is one.
glucose,
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 and then
talose.
Glucose is one.
Makes sense. There's only, what is that? Oh, and the L versions of each of them? No, those would be epimers of the L version of, so there'd still only be 4 epimers.
They flip all of them, right?
Yeah, everything flips. Yeah.
I'm looking at those that are on the slide, not all that you can come up with in your brain.
Yeah. So it's altrose, glucose, glucose, and talose. What about what?
I know.
Glucose.
Those would be
And
epimers of the L version of allos.
As well,
I do.
We've got talose. That's how I think of it.
So it's like, they just kind of flip on
They just, yeah.
I mean, well, that was named first.
Well, I remember looking at it, but I don't remember the rules.
Carbon
Because
and
right,
40
and the
things.
bottom one the left.
I
see what you're saying. And then you're supposed to count it in which way it goes.
Order of priority.
Yeah, so. You're right.
Okay, let's see if you can check yourself. How'd you do? First one you should come up with was the altrose, right?
Yeah.
Good. Next one, the glucose. Did you notice the glucose was in green? That's because you'll memorize that one too, right? And then gulose. Any others?
Talose.
No.
Why does talose? Oh, wait. Because that's the last one.
Yeah, I can't have 3 moving and 1 staying the same. Yep, we got it.
Yep.
All working on it. Okay, so looking at the allos, those are the ones we are looking for. These are 6 carbon structures. Were there actually other carbons? 3 carbons, 4 carbons? Absolutely. 5 carbons. You've already seen one with ribose, right? So yes, definitely options here, okay? 14 common hexoses that we look at. Someone asked a question because they've been looking forward to it their whole life. Is Brother Bowden going to make you memorize all of the different hexoses? The answer is no. I just told you 3 that I need you to learn. That's it. Everything else I will give you and just see what you can do with it as a functional tool. Okay?
So how do you say the name of the 20 group?
Oh, great question. I always call it fructose.
Okay.
Yeah. Yeah, I know.
I think
Fructose, yeah. Hemiacetal and acetal. Gee whiz. Hemi is in Latin, it means, as in hemisphere, half. Okay? So anytime somebody's looking at this, we're just talking about halfway there. There is a reaction where we actually take the aldehyde plus an alcohol. On the alcohol, there are lone pairs there. We have the ability to come in here and to combine the alcohol with the aldehyde to actually functionally connect, and that makes my hemiacetal. It turns out that this is often done as we cyclize. It turns out that there is a way to continue that reaction with yet another alcohol, which can add another group, and now I have 1, 2, 3 R groups from my first one that have been added, leaving just a hydrogen left in the other functional group. That is the full acetal. You will also see that we go there, okay? If I had done that with a ketone instead, same reaction, hemiketal, then full ketal, okay? Slightly different mechanism in the way that it gets there, but generally the same thing. If you want to go through the mechanism, it's awesome. We're gonna protonate this aldehyde. That sounds like a good approach first, and then we're gonna come in with the alcohol. we're gonna do a backside attack on something that's really quite intriguing, that we've got this structure temporarily there all together. And that will combine this to make my hemiacetal group, and then we'll deprotonate it finally so I can really call it a hemiacetal. And that looks pretty good. That would be that first reaction that we'd be doing. And then if I keep doing that, we can come back and we can remove the water and finally get to nucleophilic attack and get all the way up to my full acetal if we want. I showed you that mechanism, but you don't have to memorize, because you're just gonna have to use it, okay? In which we will take, is this D or L?
D.
Okay, I'm right, and, yep, okay, that's my D. And so these lone pairs are going to go where?
To the carbonyl, the anomeric.
They are
carbon.
attacking this carbonyl, okay? All right, so that is the approach. This means that we're interested in what is known as the anomeric carbon. And so as we cyclize these, the anomeric carbon becomes one of interest to us. We can have it go alpha or beta. Someone will ask, and so we will say it enough times that you don't have to ask. There is no way to know whether it will go alpha or beta unless somebody tells you that's what they want. Nature chooses at random. You cannot forelook at the structure and say, it's gonna go this way. You don't have that luxury. There are statistical probabilities where we know that they go 70-30 or, but it just is the way it goes. It's a random game, okay? So what is the alpha? What is the beta? If I'm looking for alpha, I am looking for trans across the ring wave, okay? If I'm looking at the same size cis, so let's see what we're talking about. This is alpha. We're looking at trans. So this hydroxyl, this is the anomeric carbon, okay? Where did the anomeric carbon come from? Let's see if we can identify the anomeric carbon. What number carbon is it there?
It's not numbered.
It's not numbered.
The anomeric carbon's the carbonyl.
It's the aldehyde
Yeah.
with the carbonyl, okay? So that's my anomeric carbon. Where did this oxygen here come from?
Carbon 4.
In this structure, it came right here from carbon number 4, okay? So this is also interesting. When I said this D sugar, okay, when we did that attack, it was already known the way that I would list that. Off of carbon 4, there's the oxygen. This goes up if it's D in the way we write this structure that we're going to talk about Haworth projections, okay? If I had gone beta, what would I be looking for? These are trans. What do I want for beta?
Just be cis.
Cis. I want cis configuration. Okay. What?
So it's the hydroxyl group, whether it's up or down.
Yeah, but what happens if I went, if this was up, this said what?
That you're D.
That I'm D, but what if it's down then?
Oh, then
It
it's
must have been L. Well, then in respect to this, if this is on opposite sides of it, what is it?
That's trans.
It's trans. That means it's now
Alpha.
alpha. Oh. Or cis. So you've got to think about whether it's trans or cis. Okay. Most of the time you're going to be working with D sugars. So it's really pretty easy. Some people like this way, and it's wrong, but it's fun. Okay? This may help you keep it straight for a little while. Oxygen looks kind of like a balloon. Well, some people say, hey, before the party, the balloons are up. After the party, the balloon goes down. Okay, that sounds great. Except for really, I'm interested in cis and trans. Okay?
You would accept that on the write-off?
Yeah, no, you want the right answer, that's for sure. Because you'll see stuff that'll mess you up otherwise. But it's a good place to start. Okay. All right. So, this is called a Haworth projection. In the Haworth projection, this darkened line means this is coming towards us. You will not be asked to darken in and thicken the line, but that's actually what a true Haworth projection would look like. We'll just accept that this is a Haworth projection as far as we're concerned. Cyclized ring structure, okay? Whether it's alpha or beta. Tell your neighbor how from this step to this step or this one that I would know that it was going to be alpha or beta. Tell your neighbor that answer.
Well, that was good.
Man, biochemistry is easy. All you do is guess.
Yeah, but as you said,
We can't, yeah. Did you vote?
The dangerous guessing.
I'm just gonna guess right now.
How do you know if it's alpha or beta?
That'd be fun.
How do you know if it's alpha?
Okay, if you answered, there's no way to tell, Brother Bowden. You're right. Okay? Not from the structure, you can't say this is what it will do. If you were looking at the mechanism, you could say it's going to be this based on whether it's top side or back side of the carbonyl. But you don't have that luxury. You're just looking at something linear now going to a cyclized form. So you cannot tell. But if I ask for alpha or I ask for beta, you've got to be able to give it to me. Okay? What else changes in this? If these all started here with the glucose, and then they got down here to alpha or beta, what is different between these two alpha and beta glucopyranose?
We're talking.
Say nothing, Brother Bowden. The only thing that's different is the alpha or beta. Now, write it in your notes so you don't get it wrong on the exam. I don't know how you're going to do it, but don't get it wrong on the exam. This is called an anomeric pair, like a pair of socks. This has nothing to do with D or L. They are both what? It's up, they must be D. If I had one D and one L, that is not the anomeric pair. The anomeric pair is the alpha and beta off of what? The anomeric carbon's the only thing that changed.
Yeah.
Okay. Feeling good about things? You feeling good about things? Do you think you could cyclize some of these? That looks pretty easy to do, right? Come in here, use this lone pair of electrons to attack this. Do you notice that I am using a lone pair of electrons to attack that carbonyl? And I need a carbonyl. If it were not the case, can this attack all these alcohols? No, it has to be a carbonyl. That will be important going forward. You need it to be a carbonyl. That's what you're attacking. Okay? All right. So, the rest of the information you need before we practice for the next 15 minutes. If I take this the way it is, and it's on the right side, okay, not worrying about the one that defined D or L, if it's on the right side, where did the OHs go? In my structure down here.
Down.
every time it goes down. If it was on the left, the OHs go up. Everybody good with that? Now let me introduce what's going to be messy for those of you who've gone forward, and then you'll start to see it later. This is a structure, right? This is the common way we draw it. What would happen if I took this structure and I turned it upside down?
So I was just wondering about that.
What will happen? Tell your group. What will happen if I turn this upside down like I was flipping a pancake?
So then it looks like it would be
What happens to all these groups?
opposite.
Everything gets flipped around.
I rotate it in three-dimensional
But it's not. I
space,
think
what
it's an
happens?
anti-mark.
Well, I think as far as the facial projection goes, it just flips.
But it will make the
But
living
it would make
Everything
the
flips and not just one stays the same.
down.
Yeah, then it's
Same
same
sugar.
like the oxygen would be on the wrong side. Like
No, like, cause
Yeah,
that
I mean,
would
but
be.
that's okay.
It's like a chair confirmation, guys.
GG on my
It just changes it to L.
Oh, you're right, you're right.
Does
Yeah,
it?
Like,
yeah.
everything flips, like,
I don't know about that.
All of
But all of them.
So in other words, you get
Functionally, it's the same.
Just flip it over.
Would it just be the same structure? I think it
Same
just
structure. D to R.
would that be
It
right?
would still be six.
right, that's just like one kind
Oh, we know it's the same. Yeah, you're right. It's D
but
to
he's not
R.
flipping just
So if you
one.
have that
Yeah.
same structure and you flip, right, that means 6 has come to where 3 is.
Yeah.
You're right, it's the same structure. Yes, you just have to count. You just have to count it backwards and think about it upside down. Yeah.
Yeah, check out those.
Yeah. and-
No, it would be down, but it would be on. It would still be.
Which one of
But that's
these
what you go to system.
is this? It's the beta, how do you know?
So it's cis to each other.
Yeah.
It's the one we looked at. What would have happened if I had turned it instead like this?
Oh, no. Still six.
Same thing, but the O is in a different position. We will see that. It's not about Brother Bowden. The textbook is loaded with it. All the literature is loaded with it. It is just the way it is. If you struggled with turning something upside down and seeing where they went, what's up is now down and what's down is now up, and it's, did this change? Is this now L instead of D? No. It's still D, nothing switched. All I did was on paper flip it. Same thing. Okay, you guys, you have all the knowledge you need, okay? And yes, you'll also need the ribose, the glucose, and the fructose. We'll learn those. This is called a furan ring, furanose ring. We'll get back to those in just a little bit, okay? What I want to do, we'll come back to that. Yeah. Okay, maybe I'll tell you in just a second. Okay? It's so fun. Did I mention I keep bees?
Yeah.
It's honey. This is how you will learn to draw fructose. We teach you to draw fructose wrong. I'm going to teach you to draw it wrong because it'll be perfect for you for second semester metabolism and most of what the world will show you of fructose. This, furan and furanose rings, what is the most common form of fructose?
Wait, how do you have a fructopyranose?
The predominant form of fructose is the beta D fructopyranose, with the beta and alpha furanose constituting 27 and 6%. So these are the 27 and 6%. What's the predominant form? 67% is in the beta D fructopyranose form. Oh, okay. Sucrose is actually a mixture between glucose and fructose. They're put together. Turns out that's what most of the bees are gathering. When they get it there, they use an enzyme, they break it down, and they actually, in so doing, they dry it down, which is why my bees had lots of water in there, because they're drying it down to a specific percent moisture, between 15 and 19%, removing all that water. And then when they do, they'll cap it, and it will last for how long?
Forever.
Ironically, forever. Isn't that just the coolest thing? And then pull it out and eat it. All their hard work. Okay. Yeah. Okay. Yep. Is it possible to lose we'll come back to this. Is it possible to lose whether or not I have an alpha or beta? A D or L? Yeah, I could actually have to go into the ring structure. How would I know then? Well, this was still what?
Yeah,
Still D.
Yeah.
Yeah, but it is possible to lose it. Oh, okay. All right. Is honey healthier for you? Some people argue yes. This has everything to do with glycemic index. What is glycemic index?
So that like
How quickly it turns into
glucose.
and hits your blood sugar, okay? Spiking your blood sugar. So some things take a while to actually have it absorbed. Turns out honey has a different glycemic index, raw honey does, than pure glucose. It's got to break it down. Is it different than sucrose? Yes, it is. Does that make you healthier? Not necessarily, but some people argue. Your baked potato, by the way, really bad. The other part that we look at is how much sugar is in the load. So I can have something that hits with high sugar initially, but then it takes a while to get there. This is showing you glycemic. What is next to just pure glucose, by the way, on this?
Baked potato?
Oh, savage.
I am in Idaho.
Destroy Idaho.
What? A baked potato
You just like
is
ruined our
poison.
entire culture.
He's poison.
That's my
I
culture,
love
man.
them. They're delicious. But they are almost handing you straight glucose.
Really?
It breaks apart extremely fast.
Oh, and then you don't have very high glycemic load either.
Okay, so wow, not that great for you. Yeah, so careful what you're looking at. Carrots, by the way,
chips are better.
fantastic. Eat carrots.
Yeah, let's just
Carrots up there, yeah, carrots.
Yeah. So funny, huh?
Yeah. You're looking at things you're
Pizza.
like, you just told me that I could eat white sugar and it's better than my baked potato. Yes, I did. Yes, I did. Absolutely.
Man, the Lord is.
Look at your white bread. It also was worse than just straight table sugar. Yeah. Wow. Okay.
Hey, Snickers
Guys, I'm
bars.
sorry. I talked too long. Go to the board with your group. There are markers all over. Use the markers. I want you to practice drawing. I got more markers up here. Come grab markers. You just practice. And I will be around trying to help. If somebody has done it before, they're probably going to be good at it. You want to draw these sugars, okay?
all the sugar.
Yeah,